Hello and welcome to this manufacturing process technology part 2 module 9. We had been talking about the different bonding strategies that can be used between multi-level wafers, and in context of that we had learned about how plasma can be used to modify surfaces of soft materials like PDMS or other polymers by generating a excess amount of surface functional groups with which are hydrophilic in nature, like SiOH, and it would eventually result in the change in the contact angle, and because of that there would be a sort of an irreversible bonding. And what we actually learned about was a strategy where with the contact angle we could actually gauge what is going to be the bond strength. So today we are going to just summarize what we did in terms of the different etching regimes, particularly related to the plasma processes. So the differences between the various plasma regimes, etch regimes, are in terms of the different pressures which are there within the plasma chamber. For example, there is a high pressure etching, there is an ion milling which is done corresponding to the extremely to an extremely low pressure values, 10 to the power minus 3 torrs to 10 to the power minus 5 torrs. And then there is somewhere in the middle regime of pressures which is reactive ion etching. So basically in the high pressure etching the mean free path of the species is much less than the chamber size. So this essentially limits to start and stop chemical reactions which are only a few atomic layers on the surface. The overall ion impact energy is very low because of this less free path, mean free path, and the plasma is homogeneous and isotropic in nature. For the low pressure case, that is ion milling, the mean free path is comparable to the chamber size because of the extremely low pressures. The plasma used is generally to abrade the substance by sputtering out the material. So just because you are giving more distances between the particles, so without collisions happening, the particles can travel and generate a lot of velocity, so it can transfer huge amount of momentum which can actually sputter out the material or knock out the material. So the ion impact energy is pretty high, it has high directionality. When we talk about reactive ion etching, again it is a moderate mean free path, somewhere in between this ion milling on one side and high pressure etching regime on another side. The processing is primarily chemical transformation, but there is some kind of bias which can direct the chemical transformation to take place in a certain direction. So you have moderate energy of impact, and there is a degree of anisotropy which is substantially higher in comparison to the isotropic high pressure etching regimes. So that is how you classify the different plasma etching regimes. Let's look into a slightly different a set of techniques which are also known as additive techniques or surface micromachining. We had already talked about the basic difference between bulk and surface. So in this case you're basically adding different layers of films or different materials to a substrate to build up the various structures. So the first process which comes to mind when we talk about additive technique is this chemical vapor deposition process. So basically the CVD or chemical vapor deposition is a very important technique for creating thin films on substrates. The basic idea behind the process is that there are gaseous or gas phase reactants which basically would be introduced at a reaction chamber, and they would be allowed to react at a certain condition of temperature. And because of this reaction there is a third phase which is created, which is not a gas. So there are two gases or maybe more than two gases which are entering a chamber, and at a certain temperature condition there is a reaction between these gases over the substrate, and the reactant which gets the product which gets formulated is not gaseous anymore, but it is some sort of a solid which gets deposited over the substrate. So that's how CVD is carried out. So in a CVD process the gaseous reactants are now introduced into the reaction chamber. They occur over heated substrate surfaces and results in the deposition of a solid product. So therefore there is actually a sort of a momentary depressurization of the system when such a reaction happens, because there is suddenly carrying out of a solid phase from two gaseous phases. So the deposition process is signified by a sudden dip in the active pressure of the chamber, which is being continually monitored in this particular case. The other gaseous reaction products leave the chamber after the deposition successfully has happened. And there are many forms of CVD which are really based on the ambient pressure which is being used. For example, you can carry out the CVD process at an atmospheric pressure, at a very low pressure, and also with the plasma phase introduced by doing some biasing and doing some cathodic and anodic plates, so that you can have a directionality in the way that this deposition is happening. Okay. So based on that, the CVD processes are categorized into APCVD, that is atmospheric pressure chemical vapor deposition system, LPCVD, which is actually low pressure chemical vapor deposition system, and then the PCVD, which is the plasma enhanced chemical vapor deposition system. So the APCVD and LPCVD involve elevated temperatures, typically ranging between 500 to 800 degrees Celsius. These temperatures are too high for metals, with low eutectic temperature with silicon, such as gold or aluminum. And the PCVD processes have a part of their energy in the plasma, thus lower substrate temperatures can be typically used, even up to the extent of 100 to 300 degrees Celsius for depositing the films. So generally the LPCVD reactors or the APCVD reactors are large systems which are having good amount of thermal control. High temperatures can be used in such systems, and there are cooling modalities also of such system, whereas a PCVD can be a very small source where you are basically generating a cold plasma, and the temperature of the platen which holds the substrate really is not very high. You have a heating platen which would, or heating substrate holder, which would provide that temperature onto the substrate surface. The plasma itself is not going to produce any temperature conditions, and it is basically a cold plasma that is being generated. So that is how CVD is carried out. That is one of the fundamental deposition processes, where you can have a thin film formulated like to do bulk, to do surface micro machining. The other process I would like to take you across is this thermal oxidation process, which is about generating an oxide given a silicon substrate by flowing oxygen, and there are two different conditions for which oxygen can be flowed. One is dry oxygen, another is a moist oxygen. And so typically, if you are flowing dry oxygen over a silicon substrate, and you can think of the substrate to have some vibrational energy, some surface atoms would typically like to accommodate the oxygen flowing over by expanding, contracting, and so the oxygen actually diffuses into the lattice, into the silicon lattice in this manner, if you are holding this substrate at a high temperature and flowing oxygen over it. Now this oxygen, by virtue of it being wet or dry, creates a set of chemical reactions if it is wet, and so the dry oxygen process, dry oxidation using dry oxygen is normally lower in its rate of formulation of the oxide in comparison to the wet oxidation process, which is actually a moist oxygen stream being supplied at a high temperature. So although silicon dioxide can also be deposited by, let us say, CVD, by initiating a chemical reaction, but when we are talking about trying to do a thermal oxidation, it is trying to create a silicon oxide or silicon dioxide at the behest of the silicon layer. Okay. So it is not really an addition that we are making to the silicon layer, but we are trying to intersperse into the silicon and create oxygen implants into the silicon. So that is the difference between a thermal oxidation and a CVD grown process. So typically the thermal oxidation can be used for adjusting gaps, such as, let us say, filter pores, or some channels to increase the micrometer level accuracy in which you have been able to construct the channel. So oxide is normally reflowable. You can generate an oxide layer and reflow it so that a pore can self collapse, or a channel can get smoothened because of the oxide. So based on the type of oxidation, again, as I told you, it can be categorized as a dry and a wet oxidation process. Now in a dry oxidation process, pure oxygen reacts with silicon at a high temperature. Temperatures are of the range of about 800 to 1200 degrees Celsius, and these are big furnaces with more than one zones of heating, and then overall either they are Peltier cooled or some other means of cooling is present, and then there are big glass tubes which are typically quartz tubes which can go up to a temperature of about 1300-1400 degrees Celsius. And so these quartz tubes are used as stackers for the wafer, which are actually loaded onto a boat again made of quartz, and this boat is infiltrated into, or the boat is filled, the boat is sort of laid inside the tube, and the tube closed. Okay, and so there is a circulation of oxygen happening in the tube from some source at the back, so that gives you the basis of the oxidation. So simple reaction in the dry oxidation is basically Si plus O2 is SiO2. In the wet oxidation case, it generates water vapor along with the oxygen, and the SiO2 gets created and hydrogen gets formed because of this. So this process is much faster, the wet oxidation is much faster than the dry oxidation process in terms of the formulation of the silicon oxide layer. So I will just like to improvise the concept a little bit, because it's a diffusion process that we are talking about, and as I told you that it is at the behest of the silicon that the silicon dioxide layer gets formulated. So there is a simple case here where the density of silicon and silicon dioxide are given to be 2330 kg per meter cube and 2200 kg per meter cube respectively, and the molecular masses of the silicon and oxygen are also given out to be 28.09 kg per kilomole and 15.99 kg per kilomole respectively. We want to determine the consumed silicon thickness for a silicon dioxide film of thickness D. So obviously the thickness would vary, because you can think of that when the oxygen sets in the lattice, there is a significant distortion and expansion of the lattice. Okay, so it may not be similar to the depth of silicon being used, and there is always a bulging out of the silicon dioxide layer at the behest of a few layers of silicon that is being sort of utilized on the wafer surface. So this example is just for estimating the thickness that would formulate of a corresponding to a silicon dioxide layer to the, so that is a ratio of the thickness between the silicon dioxide layer formulated and the silicon that is consumed for formulating the silicon dioxide. So let us say that for 1 kilomole silicon we get 1 kilomole silicon dioxide. Just the simple process Si plus O2 becomes SiO2, we are considering only the dry oxidation, and for the same surface area in question. So obviously the exposed surface of the wafer would be the same whether it is silicon dioxide that is created or the silicon which was already there. So the wafer, the area won't change much, because we do not really consider the sidewise expansion of the lattice on the top of the silicon, that is very negligible. What would be more appropriate to consider is basically the lattice distortion into the atomic structure itself. And so therefore the ratio of the thicknesses is equal to really the ratio of the volumes. And let us look at that if dSi is the thickness of the silicon which has been consumed, and dSi2 is the thickness of the SiO2 is the thickness of the oxide layer that has been formulated. So that would really be a ratio of the volume of the silicon which is there by volume of the silicon dioxide, and the volumes can be estimated given the density and the molecular masses. And so we can say that the the volume of the silicon is the total mass of the silicon that is present divided by the density of the silicon, and the volume of the silicon dioxide is the total mass of the silicon dioxide by the density of the silicon dioxide that is present. So let us actually look at what are the different aspects, or what are the different things which are given here. So the molecular mass of silicon has been given to be 28.09 kg per kilomole. Okay, so we can consider let us say for 1 kilomole of the consumed silicon, there is actually exactly 1 kilomole of the silicon dioxide through this reaction chemistry that has been given. So we consider only a kilomole worth of material, or kilomole weight of material, quantity of material, I am sorry. So 28.09 divided by the density of the silicon, which is 2330, would give you the volume of the silicon in meter cube. And let us do the same for the mass of silicon dioxide, which is actually 28.09 for silicon plus twice 15.99 for the oxygen, because there are 2 moles of oxygen atom, and then divide by the density of the silicon dioxide, which has been given out to be 2200 kg per meter cube. So, this many meter cubes of silicon dioxide. So, the volume ratio now between silicon and silicon dioxide comes out to be 0.44, meaning thereby that the amount of thickness of silicon that is being exhausted to have exactly an unity in terms of size of silicon dioxide layer is only 0.44, or 44% of thickness is exhausted to get 100% layer of silicon dioxide. So, obviously, there is a huge amount of distortion because of the plugging in of the oxygen, and we are not really considering the side distortions because that would enhance the area, because normally the tendency is to sort of bend the own lattice rather than going to expand out, and even if there are such expansions at the grain boundaries available at the cornermost grains, they may not be very high in comparison to the area value of the whole wafer, and a wafer size could be something like close to about 4 inches or 9 inches or 12 inches, and so it is a circular wafer, and so that area is quite expansive in comparison to the small area which would sort of expand because of exhaustive in comparison to the small area which would come because of expansion of the silicon dioxide lattice. Okay. So, that is how you calculate the difference in the depth of the silicon oxide and silicon on a first principle basis. So, let us now look into another aspect which is again another additive method for doing MEMS, and that is basically the deposition of metals. And the first process which comes into the mind when we talk about deposition methods is thermal evaporation. So, in thermal evaporation, typically done for different kind of metals, the raw material that is used of the metal is a pure wire of the metal that you want to thermally evaporate, and this wire is actually bundled together. This is a small wire, so wire because then again the surface area is more prominent and the heat transfer would be higher. We want to sublimate the material, that is the goal here, at a high vacuum, so that we do not have any impurities within the chamber, and the sublimation would result in a direct state conversion from solid to gaseous, and this gaseous products would then be thrown upon the substrates which would collect these vapors together, and that is how the metal would be imprinted on the top of this substrate. So, let us look at this process here. So, you have a inverted bell jar, and there is something called a boat, which is like something which holds the charge. It could be either a crucible, or in most of the cases it is some kind of a very high temperature resistive wire, generally made of nichrome or some other suitable alloy, which would be able to, or tungsten, which would be able to go at a very high temperature, almost at the level of red heat of the material concerned. So, several such wires of the metals which you want to deposit are now converted into balls, and these balls are now placed within such wire boats, and this wire is heated by I square R, by passing a large current to almost white heat. So, what would happen typically is that the material which is actually loaded now on these all different wires, like for example, you may have a platinum, or you may have a gold, or you may have, let us say, titanium wires. So, they would actually directly evaporate. So, there would be vapors generated from this crucible, and these vapors would go and sit now all way around this bell jar, and there are certain substrate holders here where there would be the substrates which are inverted upside down facing this vapor which is being evaporated. So, this vapor goes and sits on the top of these substrates. That is how the deposition is carried out. Now, if supposing you had already performed a step of lithography earlier to this substrate, where there is, let us say, a resist which is already laid out with some vias where the silicon is exposed and some other portions where the resist is covered, you can actually have very thin lines of metal by doing this sort of lithography and lift off. So, the resist can be taken off later on using acetone, and there are only these lines, these small lines of metals deposited on the silicon surface or on the substrate surface. So the evaporation deposits thin film on a substrate by sublimating the heat source material in vacuum. The vapor flux from the source coats the surface of the substrate, and based on the various heating sources, the various evaporation techniques that are done is normally the resistive process is known as the vacuum thermal evaporation or VTA. Obviously there has to be a backing and a roughing pump, because you have to take the vacuum of this region down to about close to 100 millitorrs, because obviously you need a very clean atmosphere for carrying out a deposition of metals, because otherwise if there is oxygen and if there are other impurities, there is always a tendency of the metal film that is getting formulated to have impurities, and the conductivity may not be as high as pure metal. Okay, so therefore you need to really do it in a very high vacuum level. The source could be changed from a wafer boat as you are seeing here, or a wire boat as you are seeing here, to a beam of electrons. So if such a sort of process exists where there is a e-beam which is heating the crucible containing some pellets of materials, then that we call them e-beam evaporation process, or sometimes you can have reactive evaporation process. So these are different variants of the vacuum thermal deposition process of metals. So if you have subsequently 2 or more metals working together, you can actually deposit an alloy as well with a constitution or with a percentage constituent of both the metals depending on the melting point. So if supposing one has a slightly higher melting point than the other, then there is a tendency of you could actually get a composition of certain percentage of one over the other in the final alloy state of the material. So that's how you do one additive manufacturing process, that is deposition method. So you have already seen CVD, chemical vapor deposition, you have seen how you can deposit metals. The other very important method which is carried out almost always, and it's very high throughput method, is a sputtering method, where the problems which are associated with the VTA or the vacuum thermal evaporation is completely eliminated, because now in the vacuum thermal evaporation the only problem that happens is that the films are not very well formulated or very well deposited, and there may be, if you are not using very clean substrates etc., there is a tendency of these films to not adhere and come off the basic substrate. So alternately you use a method which is more directed and which has sort of a momentum transfer associated with its processing, which is known as the sputtering method. The sputtering process is carried out with plasma under very low pressure, about 5×10⁻⁻⁷ torrs. So this process involves low temperature, which is contrary to at least some of the CVD techniques like APCVD or LPCVD. And the plasma is made, as you know, of positively charged ions and electrons, as I had earlier illustrated. Can be produced by high voltage DC sources or RF sources, or by fluctuating fields by inductive coupling. So the positive ions of the metal in the inert argon gas carriers bombard the surface of targets at such high velocities that momentum transfer on impingement causes the metal ions to evaporate. You can see that happening here. These are the 2 targets or target electrodes, target plates. So there is a argon atmosphere created where there is argon ions and there are electrons, and basically the substrate has a bias voltage, so that you can have all these ions, these argon ions, going towards the substrate. Let's say if we make it negatively charged here. So what would typically happen is that the electrons from the plasma would generate a positive metal species, a positive metal vapor, M+, and then there is an argon atmosphere as well. So basically there is a huge transport of this knocked out metal species into the substrate from the bias voltage which has been now provided to the substrate size, and instead of a passive coating as happens in case of vacuum thermal evaporation where you are simply depositing, here is a case where you are driving the metal ions onto the surface so that they can deposit by impingement. Okay, so there is a higher strength that formulates of these films. So it's a high throughput method, because mostly in sputtering you can actually deposit thick layers at least up to several hundred nanometers. And also the other issue is that you do not have to really jeopardize the mechanical strength of the film, because there will be a solid film formulated on the surface of the substrate. However, there is a downside of sputtering process, which is in terms of when we talk about a combination of lithography and sputtering, if we do not have the right parameters for a sputtering process, there may be a possibility that the film of resist, which is actually coating, which is a sacrificial mask coating onto the substrate surface, may get damaged, sometimes very highly cracked because of the continuous action of ion bombardment on the surface. So, if I wanted to do sputtering for a very long time over a lithographed wafer, there is going to be a possibility of the resist film cracking, and that may result in some kind of jeopardizing the overall structures which are laid out in the MEM. So, you have to be very careful about time control of the deposition whenever you are talking about sputtering method. So, although the upside is that you have a high film strength, you have a greater yield, but the downside is that there may be a cracking of the sacrificial mask, for which there may be a possibility of using some sacrificial hard masks rather than soft masks, like let us say silicon carbide, etc., which can later on go into another process like deep reactive ion etching, where that carbide can be removed completely through a gas chemistry. So, that is how you do additive again methods for additive micromachining. The other very important aspect that I would like to discuss with you is again doping and ion implantation. So, as the name suggests, basically impacting of certain ions onto a silicon lattice. Now, silicon can be doped into an N type or a P type. I think most of us are quite aware of what is an N type or what is a P type, depending on the group of the material that we are doping. So, one should have 3 electrons, another should have something like boron, and another should have something like 5 electrons or something like arsenic, where there is always a tendency of either one excess electron or more excess vacancy hole formulated from a 4 electron configuration of silicon crystal, which is there in the lattice. So, the ion implantation technique is one of the most important techniques again for microelectronics, and adds impurities to semiconductors such as silicon. So, it basically changes the resistivity at different times by inducing certain defects, and in ion implantation the ionized impurities accelerate through electrostatic fields, strike on the wafer surface. You can think of this as a ion implantation process, where you have a, let us say, a target which is somewhere in this region, and there is a huge ion column which is having an ion source at the back end, and an accelerator where there are magnetic fields and electric fields which are placed so that the ion sources can get screened off, and then there is a mass separation by applying a magnetic field, so that you have different directions in which the different ions can sort out. And so, you have one particular ion sorting out in a particular direction going to hit another tube here, which is again accelerated further, so that there are high energy ions of a single kind available at the top of this substrate, which is somewhere here. So, the dose can be tightly controlled using ion currents, using an ion current, and the dosage from the process range from 10 to the power of 11 molecules or atoms per centimeter square for very light implants, to about as high as 10 to the power of 16 atoms per centimeter square for low resistance regions such as contacts, emitters, buried collectors, as in transistors. So, by controlling the electric field, the penetration depth of the impurity atoms can also be controlled, and the typical amount of or typical kind of gases which are actually used for the purpose of generating the the different ions, whether it is boron or arsenic or phosphorus, are BF3, arsenic hydride, ASH3, phosphorus hydride, PH3, etc. The separation by this method resulting in a implantation of oxygen can produce something which we better know as silicon on insulator SOI or CMOS wafers. So, that is how the doping or ion implantation is carried out as a process. So, after the ion implantation, the dopants are distributed in a layer on the silicon substrate or surface, and subsequent annealing would redistribute the dopant atoms. so that you can actually even go sidewise and affect certain zones or certain regions completely in terms of layers which would cover. And as you know that these are very useful, because as I told in the bulk micro machining case, that if I had a layer of oxygen or oxide, or let's say a layer of P double plus material which is buried within some particular depth of the surface, we could use that as a etch stop layer, so that you can only etch up to that and not beyond, So those kind of situations in MEMS arrive at where these dopants are very, very useful. So for applications of MEMS, and particularly this new area of microfluidics, a much thicker SOI layer than the result, than that resulting from the CMOS is needed. So most SOI wafers or silicon on insulator wafers used in MEMS are fabricated with bonded etchback techniques, silicon on insulator techniques, where there are two such silicon on insulators which are bonded back to back, and that results in a relatively higher thickness of the handle layer. Okay, so we call it a Besoi technique, in order to produce such silicon on insulators. So the technique uses two polished silicon wafers with an oxide layer on each. The two wafers are then bonded together using fission bonding, and one wafer is thinned to the desired thickness by chemical mechanical polishing, so that the handle layer can be thicker. So there is a thicker handle layer on the top of which you have a small silicon and a small insulator of SiO2. So that's why it's called silicon on insulator. So the main advantages of SOI fabricated using this technique is the thickness of SOI is adjustable, allows thicker structural layers of the device. Thickness of silicon dioxide is again, you can go up to higher values, and the SOI would have the same quality as the bulk substrate. That is a big challenge, how to match the SOI crystal with the bulk substrate. And the other method which is used, CMOS, is actually slightly different variant, but it produces a lot of crystal defect. And I'm not going to cover this because this is going into a lot of microelectronics. So that's about what I needed you to sort of see when you talk about the non-conventional first generation processes borrowed from the microelectronic industry. So in summary, you have made a study of the different subtractive techniques, the different additive techniques, the use of plasmas and the role of plasmas in doing etching as well as deposition. So with this I would like to end this particular module, and in the next module we will start a very interesting process again, which is the first sort of new non-traditional process, which although exists from centuries, but we will look at it from a more modeling perspective. That is the abrasive jet machining, or AJM process. So with this I will close this module. Thank you so much.